So I'm going to tell you about Cogsketch. Cogsketch is a sketch understanding system. And it was done as one of the products of the Spatial Intelligence and Learning Center, SILC, which is an NSF Science of Learning. Now, these centers are 10 years in length. And so when we started in 2006, we thought to ourselves, this is a rare opportunity to actually do something for 10 years. So what should we do? Well, so some of us, not by no means all, but some of us basically said, well, look, if you think about intelligent tutoring systems, they're very useful in education because they can give feedback to students immediately, anytime, anywhere. That's a great thing. They've been demonstrated to be useful in a lot of domains, but where they haven't been usable is in things that are spatially rich. So engineering, biology, geoscience, all of those domains have not been tackled with this sort of technology. Why? Because it requires a deeper understanding of spatial reasoning. And so without spatial reasoning and without the ability to communicate spatially with computers the way you would with a person, i.e. sketching, you're not going to make that work. And that in turn raises a bunch of very hard scientific problems. So for instance, you have to model human-like visual reasoning. The software has to see things the way we do. Otherwise, it's not going to work. You have to model the interaction of spatial and conceptual reasoning because domain knowledge is involved in these domains. So our idea was Cogsketch. The idea was we're going to do the basic research needed to create the science base for building such tutors, and along the way, we'll use the same software as a platform for building new kinds of sketch-based educational software. That was our vision, and that's what we've done. So, understanding sketches like people do. So here's a ramp that someone, ramp and a block and gravity. And now when we're drawing together, I'm telling you what these things are because Lord knows I'm not an artist, and I'm not an artist in real time, even if I were an artist. And so I've conceptually labeled those things for you. Now, once you know what they mean, I can say what's going to happen next, and then you can say, well, the block will slide to the right and down. Okay. Very simple, very easy. And what you'd like is to have a system you can sketch with that have natural fluent interaction, the way you would with another person, human-like visual and spatial reasoning, so again, it understands things, conceptual reasoning about the sketch. You didn't have to have a bunch of numerical values here to do a simulation. You just knew what it would do qualitatively in simple conceptual terms, and you want it to be domain general. If you look at what most people think about sketch understanding today, they equate it with sketch recognition. That's a big mistake for several reasons. One of them is that in most domains, there's not a one-to-one mapping between shapes and objects. Think about someone saying, I'm going to make you a symbol for a room. Whoop, not going to work, right? And in fact, in almost every STEM domain, with a few exceptions where you've got abstracted visual symbols, electronics diagrams, digital circuitry, and a handful of others, then you can do sketch recognition. But in every other part of the things you use sketching for, in science and technology and engineering and mathematics education, aka STEM, it doesn't work. And what that means is you don't have domain generality. So we decided early on, no sketch recognition here. Instead, we're going to focus on all these other things. Now, to do that, of course, you have to have some hypotheses. And our two big hypotheses are this. First is that one of the jobs of perceptual processing is to construct what we call qualitative spatial representations. If I'm going to drop this thing, there's a big difference between dropping it on the table versus dropping it on the concrete floor. And so this actually imposes a piece of space you can think about because of the constraints it's going to impose on motion. Well, that's the heart of the idea of qualitative spatial representations. They're very powerful, they're very flexible, they've been used to capture a lot of scientific and engineering reasoning by qualitative reasoning research, And in fact, in cognitive psychology, it turns out they came up with a similar distinction, categorical coordinate, and they worry about things like how you store stuff in long-term memory, which we never care about. So what does that look like? Well, there you go. Here's an example of how Cogsketch actually works through that problem we just did. You're going to see the insides of Cogsketch's head displayed in the kind of concept map representation. This is literally the chains of reasoning it went through. So you've got entities representing the ramp and the block, the conceptual interpretation of those pieces of ink. And it reasons that, well, these things are touching directly in the sketch, and because they're touching directly, there's a surface contact, and it visually constructs this surface contact. So it figures out where that is. And then since it's reasoning about force, it's saying, well, I need to know the surface normal, and that's in quadrant 3. You can see quadrant 3 right here. It's basically going that way, which is where the block is going, if I get out of the way. And now then what happens is you have to think about gravity to know what it's going to do, because you think about forces. So we have this gravity arrow, and the force is being applied to the object, and since it's going in this direction, that means it's going down. Now, if you think about the force going down, it's the only force applied to it. And so we do a closed world assumption that the force on the block is that force going down. Now then, because there's this translational constraint because of this surface, you basically have a constraint in the downward direction, and that plus this basically lets you figure out that it's a translational motion in quadrant 4, which is to the right and down. And that's the reasoning we got. No numbers, no numerical simulation, very conceptual, but essentially visual. If we couldn't actually look at the sketch and identify that surface contact and think about it qualitatively, the rest of this reasoning doesn't work. So, second big idea. Structure mapping processes are used in visual reasoning. Structure mapping is Edward Gintner's theory of analogy and similarity. Analogy and similarity should have to be the same thing psychologically. They operate over what we call structured relational representations. The same theory has been used to model scientific discovery, conceptual change, high-level visual processing, aspects of auditory processing, metaphor interpretation. It's been used to explain a lot of laboratory data. It's been used to predict new findings psychologically. And we have computational simulations of analogical matching and retrieval and generalization that, again, have been used to model human data and predict new data. Now here, if you think about visual solving, and this is all the work of Andrew Lovett, one of the grad students in Silk, geometric analogies, an ancient paper by Evans, 1968, looked at geometric analogies. If you download Cogsketch, it's publicly available on the web. There's a sketch that includes all of the classic Evans examples, and you can run a model on it and see what it does. You can even see how it's computed. Is it computing the answer by computing A's to B, figuring out the similarities here, and then projecting from here to construct an answer? Or is it doing it by a second-order analogy? It has both methods, and the fact that it has both methods lets it match human data with an R-squared of like over 0.9. Okay, it's a ridiculously good fit for human data. There was an experiment by DeHaan and Spelke looking at geometric processing in Americans and Munduruku, an indigenous South American group. They behave very differently. And interestingly, again, Cogsketch, what's hard for Cogsketch is hard for people and vice versa. And by doing ablation studies on the software, not the people, obviously, then you could actually capture those differences and give an explanation about why. A very general, widely used test of fluid intelligence is Raven's progressive matrices. It's interesting because it requires a lot of re-representation. You have to look at something, break it apart, and glue them back together in different ways. That's what makes the problem hard. As there's a whole test of these things, the Cogsketch model performs at the 76th percentile, which means it's better than most adult Americans, okay, on this exam. That does not mean it has more fluid intelligence than most adult Americans, okay? But you have to always interpret these things carefully. In terms of human level performance, it does very well. It makes reaction time predictions that have been borne out in laboratory experiments, And a paper on that is just got accepted for site review. And there's also looked at paper folding, which is if I take this piece of paper and fold it up into a 3D shape, do those two arrows touch or not? There's 10 different classes of problems. The simulation handles all of them. Mental rotation, which, by the way, you can't do these problems unless you could do mental rotation. The model there also involves analogy. First, a qualitative mapping based on the qualitative representations, and then based on the qualitative interpretation, it then does the more exact mapping quantitatively. It's interesting, you look at the mental rotation literature, how do you know which way to go? The answer is this rapid qualitative match provides that. And so in terms of individual differences, there's some people really can't handle complex problems, others seem to handle problems in time independent of the complexity, and Andrew's got the first, I think, really solid computational explanation for that. Now, if all we could do is visual problem solving, that might not turn into being able to do problems in various STEM domains. And again, we're doing broad generality here, so that means we need to test it in a bunch of different domains. And we by no means exhausted science and engineering, for heaven's sake. Those are huge. But we've done various point experiments. And since the software is available now, people have used it in other systems, and we're making it open source within the year, hopefully many more people will pick it up and play with it. So, if you look at conceptual physics textbooks, they have problems like this. I've got a stump, and I tie two ropes, and I want to know which pair of ropes is exerting the most force on the stump. How many do you think the first one? Second one? Third one? Yeah, good job, good job. Your distribution is very, very excellent. The middle one, right, because the parallelogram law of how forces combine. For learning how force works, you can use Cogsketch to make comic strips. So here's a little 4-panel comic strip that shows a ball being kicked and what happens. By giving it just 16 of these sequences, a companion cognitive system, one of our cognitive architectures that uses Cogsketch among other things, can use analogical generalization to learn models of force, and the trajectories it goes through are similar to those of human students. For instance, if you were to ask a child at a particular point, hey, is the table pushing on this projector? Their answer would be, well, of course not, because then it would be going upward. Okay. And Cogsketch falls for that misconception during parts of its learning cycle. We've also used it for learning by reading. So Kate Lockwood, in her PhD thesis, took a book from a Navy manual on how levers work, simplified the English so that our third grade level natural language understanding system could deal with it, sketched the diagrams, and by using analogy with examples as the way of reasoning, after reading the chapter, the system was actually able to correctly answer 12 out of 15 homework questions for that chapter. Okay. So it can do STEM reasoning and learning. Now, it uses rich relational representations, hierarchical relationships, which is kind of a long history in the vision community. Wherever possible, we draw on vision science. And if we don't have vision science evidence, we do the best we can. So, for instance, you got these three entities here, which you can think of at the object level, two circles and a square, but you can also group them using Gestalt principles. So these two things are the same shape, and so they're probably part of one thing, and that's probably part of another. You can also decompose the ink you give it. So if I drew a stack of blocks, you notice I really am no artist. Cogsketch's visual system can carve that up into edges and junctions, and then turn those into edge cycles, which are kind of prototypical things that could turn out to be surfaces, depending on what the object actually turns out to be, and edge cycle objects, which are a way of segmenting more complex things into pieces. So the goal here is we're trying to see sketches as people see them. So if you're an architect or an artist, you look at something and you see various things. Now your student doesn't quite see the same things as you do. But in fact, the overlap is huge. Because you're both mammals, you're both primates, right? Same species, not a lot of differences there. And so there's still this big overlap, but there's this expertise, and there's misconceptions, and so there are differences. Now, poor Cogsketch, instead of this finely tuned biological brain substrate, it's running on a highly organized piece of beach sand, so it's more like down here. Okay? But as long as this overlap is big enough, it can still be useful for education. And so we actually looked at two different ways to use it in education, just again to make sure we're being general. These aren't the only two ways, by any means, but they're intended as demonstrations. So the design coach is aimed at sketch anxiety, a problem that some of you have hit upon. Okay, engineering students have it too. Some of the instructors, well, one of them actually is very vivid. He says, I want to stand up on my desk and scream at them, sketch, damn you, sketch. And I've seen it. There's a group, they work in groups of 4 with real clients. So this is an example from the Rehabilitation Institute of Chicago, where the problem is, how do you have a stroke victim clip their fingernails with only one working hand? Right, clipping the bad hand is easy. You can kind of put it where you want it. Clipping the good hand, that's the problem. Okay, this is one of many designs, and the student's job is to explain it to Cogsketch. Okay? It's not threatening to explain to a piece of software. It's just a piece of software. So they draw the different states it's in. Those states, again, they draw the relationships. There's a little language-like interface that lets them put in more deep explanations of it. And when Cogsketch can't get it, it actually says, whoa, wait a minute. You said it's going to do this, it's going to do that. And then they iterate. We used the notion of sketch anxiety by analogy with math anxiety. Sion Blaylock at University of Chicago is one of the SILT people, and she helped us design a measure for this. And with just one Cogsketch design coach exercise in a pilot study, significantly decreased anxiety in students in sketching in an engineering context. So we're pretty happy about that. Now we put most of our work on sketch worksheets because this is a problem for the engineering design students, but as a total fraction of college undergraduates, that's pretty small. And so we wanted something that could be widely applicable across all sorts of domains, but very simple. And so we wanted to hit all sorts of domains, but also all sorts of ages. And there again, we turned to analogical reasoning for generality. So let me show you the sketch worksheet model. So sketching is, of course, a great way of describing relationships. This is a problem from Andy Jacobs' geoscience class. The sun is radiating the earth irradiates heat, and the student here so far is missing the idea of the greenhouse effect, where the the atmosphere radiates back to the earth. So they're a great way of communicating things, but the feedback is delayed. Now in Andy's course, when he gives problems like this, the students get it back in a week. In the design thinking communication class, they're given a bunch of hard exercises to do to learn engineering graphics drawing towards the beginning of the quarter. A quarter is 9 weeks long. Some of my undergraduate advisees report they don't get their sketch homeworks graded and turned back until the last day of class. Not going to learn much from that. Okay, so you really want instantaneous feedback. Now Cogsketch can provide on-the-spot feedback. This example is actually in the distribution, so you can try it out yourself, and you'll see literally this feedback, where it's basically saying, gee, atmosphere helps warm the planet, I don't see how that happens, some things to think about there, okay. And the key thing is sketch worksheets can be built by instructors. Don't have to be an AI person to do it, okay? Because if you do, it's not going to travel very far. NSF terms, translation, dissemination. So here's how it works. Let me show you, let me go under the hood, and you'll see exactly how it works. So the teacher makes a sketch, which is intended to be the answer. The answer, it's a little more complicated than that, but let's just leave it as the answer for now. Here, Bridget Gagne is a geoscience grad student at University of Madison, Wisconsin. She, with the help of her geoscience faculty supervisor, Basil Teakoff, generated 26 sketch worksheets aimed at covering all the topics you would want to teach in an intro geoscience course. So she generated them, we didn't. Very important. Now, when she does her sketch, Cogsketch does its analysis of it, produces a bunch of these representations, and then she marks some facts as important. And if that fact is missing, what do you say to the student? So that nice, long, complex English explanation wasn't a result of subtle reasoning, it was a result of what she typed in. Now you might say, from an AI perspective, oh, that's cheating. I don't care, okay? Because this lets the instructor customize things. You want to make things age appropriate? Perfect. You want to teach in a language other than English? Great, okay? You have control. And again, if you can't let them control that, it's not really going to spread. So now Cogsketch does this analysis, and because they've marked this stuff, they can also say grading, if this fact, important fact is missing, how much do you want to take off? Okay. Now the student does their sketch, and the same analysis is used. So if Cogsketch can't see the important thing, she's going to know here. But if it can see the important thing, and we do our job right, it's going to be visible here. And so we take the two sketches and pass them into SME, our model of analogical matching. Now, if you want to find differences, turns out analogy is a great way to find differences. Finding differences intimately linked psychologically to finding similarities. We can talk about that offline. It's a pretty cool phenomenon there. So it finds differences, and some tutoring rules in the coach basically help you figure out how to prioritize these things. Don't give them hard things before easy things, for example. And then that gives advice. And of course, that advice goes back to the student, which it might be 3 a.m. in their dorm room when they're doing this. You do not want to be there yourself. That would be creepy. And it also gives feedback to the instructor in the form of assessment data. So it's a computer. It can record everything. It's got all the ink strokes, X, Y, T for every point. You can look at exactly what the student was seeing when they hit the feedback button at any point. There's higher level summaries about just the order in which they drew glyphs, okay, and all that stuff. It's been used, in fact, in some psychology labs as a source of gathering data from ink, where they turn off the feedback, and they turn off some of the other facilities.
So what if the student comes up with something original? Is there any way to find that?
If you define things right, and I'm going to show you what that means in just a moment, it will be okay. Okay. The place where what we've done is put in the facility to use multiple solution sketches. So if you download Cogsketch right now, there's two things you can't do in the authoring environment. One is multiple solution sketches. Oh. Wow. That's a new bug. So one is multiple solution sketches from the authoring environment. The software supports it, but we haven't put in the GUI support for that yet. And the other is misconception sketches. So there's some cases like free body diagram problems where there's really classic misconceptions. And if the system sees the student's done one of those, you want to give some very specialized advice, ignore the other advice. So we just haven't exposed those facilities yet. So what you're getting here is not just product, you're getting process. That's the way where digital in general beats pencil and paper. If you try to do this with pencil and paper, there's some things where you're looking at particular kinds of brain damage and people are given a colored pen and every 30 seconds the colored pen is swapped out and you do video and analyzing is total pain. Whereas here, the data collection is very simple. Now, for this to be general, you have to have a flexible, visible, visual language. And you have to have the flexibility when you need it and rigidity when you don't want it. So, for instance, representing relationships, binary relationships by arrows. One of the most common conventions there is graphically, right? So here, these are radiation arrows, and this is one correct solution to the greenhouse effect worksheet. Now, as long as those arrows are pointing to the right entities, it doesn't matter what the entities look like. So, in fact, that's a perfectly good solution too. Planet isn't a ball, sun isn't a ball, well, sort of a ball, but, and these are squiggly, but these aren't squiggly. This has got stuff in it, very hazy atmosphere perhaps, okay? Cogsketch doesn't care because the instructor didn't mark those things as important. If these entities are all here and they have the right arrows between them, it's happy. In fact, another solution it's perfectly happy with is that, it's a concept map. You just write the labels for the things, but you tell it, I mean this to be the sun, I mean this to be the earth, I mean this to be the atmosphere, here are the arrows, and it's happy. So you can be as creative as you like in terms of the rendering, as long as the important facts are still true. And again, that's very important, because without this, you're telling students, and you must draw this way, you must draw that way, and it really gets in the way of them thinking about what they're supposed to be thinking about. Now, sometimes you want things to be exact. If you're a geoscientist, you're having people mark up photographs, and you don't, if this is the underlying fault, that's the fault. And so you have quantitative ink constraints to say, hey, I really mean this. I really mean this. This is really going to match this. And you can put in fuzzy boundaries, right? You can say, okay, if it's within this, I'm going to still count this as correct. In other cases, you need non-visual information. So here's a carbon cycle worksheet from geoscience. Every arrow here is a carbon flow between different reservoirs in the environment. And so you have to say how many petatons are flowing within each one. So that's an annotation about a visual thing. It's not a visual thing itself. So it's a reasonably flexible language, and I think that's very powerful. So we've used these in a lot of experiments. Over 500 students have used them in classes. Perfect. And lab experiments. In geoscience, I've seen the most use. Those same worksheets from Madison are now being used at Northwestern Geoscience, not as an experiment, but just the instructor wanted to use them. Great, that's just what we want. In fact, he's so happy with these. We were a little scared because we didn't hear feedback from him during the quarter. It's just like, no, they worked, I'm happy. I tweaked these things the following way. I'm going to use them again. Blessed saints. Did an experiment with some 5th graders in a biology classroom. Nora Newcomb and her lab at Temple did this. Luis Gomez has been doing this with students at UCLA. Got significant improvement on 2 out of 3 pre-post test pairs doing a unit on the heart. Engineering design, those graphics worksheets, now by heavens they get feedback a lot faster. Still getting some kinks out of this. It's sort of annoying. And the absolute latest thing, which isn't on here, is in my own knowledge representation and reasoning course, we got slammed with 65 students, which is way more than we usually have, like over a factor of 2. And so I said, okay, the homework's going to be based on Sketch worksheets. Think data, semantic web, okay, we'll make this work. And my TA is eternally grateful. Okay, where are we going next? Well, we're building a distributed version. The version right now runs on Windows only. And so we're making an HTML5 ink interface. Ink interfaces plural, because we're going to do some web-based scientific research with this. Also integrating it into the various web-based educational software systems that are around. And of course, people want to have their favorite device with a pen or even without a pen in the classroom. My classroom's already bought iPads, but we have a network. Great, you'll be okay. When we look at sketching as assessment, it turns out even just copying sketches can help you measure expertise by the order in which people draw things and what they choose to include and not include. And so we've been using analogical generalization to cluster sketches. You get a bunch of student sketches, you run generalization, you get these clusters, and then instruction designers and teachers can scrutinize them and try to come up with some conclusions about what's going right and wrong in the class. We're looking at teaching AIs through analogies. Maria's actually using textual analogies that come with drawings that are used with middle school science students to teach a companion about how biology works, also electricity as well. And so it's actually handling both the language processing and the sketch processing and combining the sketch and graphics appropriately. And so it can answer questions like if you say, well, what's the purpose of the mitochondria? Oh, well, it produces energy because they're like power plants, and that's something that power plants do. We're taking the next step of integrating with vision, and you have to be careful because the computer vision community is not where you'd like it to be. So here's a sketch from a science book, a drawing from a science book. Here's an edge finder running on it, and here's the next stage down. Another diagram from a science book. So we're not trying to say we're going to handle the sorts of drawings that you folks have been showing up here, because the vision world isn't ready for that. There's no way today's computer vision systems are ready to handle that complexity of thing and do it justice. So you start where you can, right? And if you can build a pipeline that shows how things work, that's incentive for the vision people to do better. So we're starting with OpenCV, open source library. It produces edges. We're going from those to ink. And we're going to look at doing analogical generalization over those. We're also looking at Connect, because again, it's a sweet spot. If you're going to have a social organism, which is what we're trying to build our AIs as, then they want to actually be able to read the people that they're working with. And that's something Connect Sensor is very good at. Now, of course, we don't want to sit there and do massive amounts of real-time data computing. Cogsketch is not designed for that. Our idea is to actually make a streaming system that then groups it into qualitatively distinct things, which get turned into Cogsketch comic graphs. So for instance, here's a faculty meeting as seen in comic graph terms. You start out not too happy to be there, then you get dismayed as things proceed, and finally you just zone out. Or it could be a face palm, depending on just how bad this phase was. Okay. And finally, one thing we're interested in is, can you use Cogsketch to support creative work? On the right here, you see what happens if you give Cogsketch to Will Wright after he's had about a half bottle of Barolo. Okay. So you have your squid here, which is eating. Notice the knife and fork. This submarine, which is firing a torpedo to destroy this object, which has got satellite data coming down to it. This is by an Australian painter, Shona Trescott, and it's her two dogs taking a walk in the forest with their favorite toy, this big blue ball that they're really fond of. So imagine you're working and you have, of course, have built up a huge portfolio of ideas visually, and imagine that someone can actually get that stuff into a form that the machine can understand as well. This was, by the way, not a new idea. There's a thing called the electric cocktail napkin that tried to do this decades ago, but the problem is the vision technology at the time and the vision technology and analogy technology weren't really up to speed, okay? They tried really hard, and it was a very crude system because of the limitations of the time. Now, you could imagine something coming up to you that actually is a reminding of what you've done. We've actually built systems like this, but in the military domain. Okay, you're trying to solve a tactical problem and it thinks of a prior tactical problem, you see a little thumbnail. You can drill down the thumbnail and see what the solution was. So in outline that works, but the devil's in the details. And then as you interact more, you'd like to use analogical generalization to learn more about your visual styles. So that'll actually help refine the analogies to be more interesting and useful, but also your interaction patterns. Like, you don't want the thumbnails popping up when